Okay. Don't worry. You just like try to hear. So on our last discussion, we had got one expression XU is equal to 0.87 FYAST divided by 0.36 FCK into B. This XU is neutral axis depth. Now this neutral axis depth is with respect to extreme compression surface, not with respect to extreme tension surface, right? Now, will you be able to feel from our discussion that why the authors find the expression XPXU with respect to the extreme compression surface, not with respect to tension surface? Can you imagine or can you feel it? Okay. I will not spend much time because this is new thing for all of you. So you are not able to see this note. Okay. No. Whatever question I had raised, that question is in our assumption. In our assumption, there was one assumption that tensile strength of concrete is ignored. Tensile strength of concrete is ignored. So the tensile is resisted by tensile steel. So this is the cause, since we are considering the concrete area with respect to our compression zone. That's why all the authors are trying to get the expression for a neutral axis depth from extreme compression surface, not from extreme tension surface. Now, once we get the expression from extreme compression surface, we'll be able to find out the depth of neutral axis from extreme tension surface. It is very easy because this XU, our again I say this effective depth. What is effective depth? Effective depth is depth of the section from extreme compression surface to the centroid of the tension reinforcement. The part below the centroid of the tension reinforcement to the extreme tension surface is totally neglected. We don't assume that it is not there. It is there, but it is neglected, and that part is over. And why we require over, that discussion we had made previously. Okay, so we'll be able to find out it. That will be just effective depth minus XU. That will be the neutral axis depth from the extreme tension. Okay, so the expression is very simple. The expression is very simple. Neutral axis depth. This neutral axis depth XU is actual. Is actual. Now, so it is. No, then it is converted to an expression of ratio. XU divided by D. That means whatever D is, we had introduced a D, or what we can say, we divided both left and right side of the equation by effective depth D. The result will remain same. So we will get N XU by D is equal to 0.87 FYAST by 0.36 FCK BD. I am writing this expression. You need not keep in memory, at least for your academic part, but for your real life it will be required. This is available in your IS 456. I am writing here, which says the expression capital G 1.1 as in annex G clause 38.1 IS 456. Right. Now, when we are considering this expression, we are not considering whether stress in concrete reaches the ultimate value and stress in steel reaches ultimate value. both t value may be below the ultimate value, or one of these two may be below the ultimate. Now, if both the stress reaches the ultimate value, that means if the stress in concrete reaches FCK, and if this stress in steel reaches Fy, then that is the situation of critical. If stress in concrete happens to go beyond characteristic strength, there is a probability of failure of the member due to compression. And if stress in steel goes beyond the value of Fy, then there is a probability of failure because of tension. So we are not allowed to go beyond that. We are not allowed to go beyond that. So if the stress in both concrete and steel attains the value of ultimate FCK and Fy respectively, then the section is said to be in a critical condition. It is called critical condition, or also it is called its critical section or compressed section. So for that we require this value of XU, and that's why it is called limiting neutral axis. See, depth of neutral goes from extreme compression surface inner side of the beam. So as neutral XU increases, as X it may increase. So if it increases, it reaches value such that neutral axis means there is no stress, there is no strain. That the stress in concrete as well as stress in steel attains the permission. So for that we want to find out. Now see here, very simple. Neutral axis depth is designated that XU maximum, right? Now again we are going to strain curve. Here I have not written the value. The strain, this is the strain diagram. The strain in concrete is 0.0035, and there is a value we had considered 0.002, and this is the strain in steel. Strain in steel, and from this triangle itself we can say that the strain in steel epsilon ST maximum tension strain is 0.0 FYES by plus 0.002. So this expression, don't afraid that this expression is obtained in 5th semester. This expression you had obtained in your class 8, 9 standard. This expression you had obtained in class 9, 8, 9, 10 standard. Only from there, we borrowed it, right? Now see considering the similar triangle from the strain diagram. From the strain diagram. I have not drawn here a separate figure. If you consider that if you here you replace XU by XU maximum. Now from these two similar triangle, this is one similar triangle, upper triangle in strain diagram and lower triangle of the strain diagram. These two are similar. And what is the similarity conditions? So from this, see what we are getting. XU maximum. XU maximum. So this, that means from here to here divided by from here to here is equal to this divided by this this minus this. Now see here. Now XU maximum by D minus XU. XU maximum divided by D minus this. D minus this. So this. So this divided by this. So these two are similar triangle. So this divided by this. You see here, 0.0035 divided by 0.07 Fy. Yes, now this value I had written here. So say this. Now, if you do simplify this, I probably we had discussed in our last class also. If we add numerator to the denominator on both sides, so ultimately what you get, Xu maximum by D is equal to 0.0035 divided by this. Now see the similarity of our previous triangle. So previously, when we had considered the actual neutral axis, we had obtained Xu by D. But this time we are taking the similar expression, Xu by D, Xu maximum divided by D, Xu maximum by divided by D. Now here you see. Now here you see. Now Xu maximum divided by D. Xu maximum divided or Xu maximum is dependent on what? You observe that Xu maximum critical neutral axis depth or critical or limiting neutral axis depth is dependent on the effective depth and stress in steel, yield stress of steel, dependent on this. Okay, now from here, since this is the ratio, we got a ratio here. Now see Fy, Xu maximum by D. So Xu, if we again convert Xu maximum by D is dependent on Fy. Fy. See, if Fy is 250, then Xu maximum is 0.53, 415, 0.48, 500, 0.46. Okay, so in your examination, you may get a question of 2 marks. You will get a question of 2 marks. Xu maximum by D is dependent on Xu maximum by D or critical neutral axis depth ratio is dependent on if they are given the 4 questions, that number 1, yield stress of steel, yield stress of concrete, both yield stress of concrete and steel, none of the above. Multiple choice question. So your answer will be yield stress of steel, only yield stress of steel. Fy, because ES is constant. ES is assumed as constant. Although we had got one expression for ES in our very beginning, but the variations were different. So that's why ES is assumed as constant. The value of ES is normally considered 2 into 10 to the power 5 Newton per millimeter square. So it is constant. So it is dependent on only Fy. So this. So now these values, I told you of previous day also. So this value you will get in your high school. This will be required. Okay. We got up till now actual neutral axis depth and limiting neutral axis depth, right? So I have told you this chapter is related to your strength of material, bending stress distribution. We are utilizing. So now we are to find out the moment of resistance. Bending moment is because of the external load, and moment of resistance is resistance offered by the cross section. It is internally. Moment of resistance is internally. Now here it is given that Xu is less than or equal to Xu maximum. Actual neutral axis depth is less than limiting neutral axis depth or equal to. If Xu is equal to Xu maximum, then this section will be said as critical section. Okay, now let us see what is the moment of resistance. Moment of resistance. Moment of resistance, always you know it. All of you know it. I do not assume that you do not know it. You may forget it. You may forget it. But moment, for a moment, we require two components. One is force and another is hmm, distance, minimum distance from a particular axis. That is called lever. Now here, these two parts you see. One is 0.36 FCK B into XU. Now this expression we had got in our previous part. 0.36 FCK. This is the C, total compression, and D minus 0.42 XU. Now D minus 0.42, where it is coming. So this is the difficulties with our online class. Had it been the blackboard class, I could have been able to draw more and more figures. Now see again here, we are in the last class I had shown, at a particular point on the compression zone, the total compression X and total tension X at the location where tensile steel is there. Now, both the forces are and since both the forces are acting in opposite direction, they between these two forces, total compression C and total compression C, total tension TU, this distance is the lever arm. So since they are acting parallelly in opposite direction, they are forming a couple. So this couple, since this couple is induced on the section due to internal force, that's why it is called moment of resistance. Okay, so again I'm going to say the distance from the line of action to the line of action of the tension is the lever arm. So this value is, we had already obtained distance of line of action from the extreme compression surface, 0.42 XU. This we had already obtained. So distance between line of action of this C and T will be equal to effective depth, small d, minus 0.42. So this is the expression. In expression you will be able to see when you will get this note. So this C into D minus 0.42 X. So remember the resistance. Before the moment, no other word is there. That means this is moment of resistance with respect to a particular situation. With respect to a particular situation, not a constant situation. Okay, similarly, moment of resistance with respect to steel. So it is the ST. This is the total tension TU, and lever arm remains constant, right? Okay. Now see here, these are the some manipulation. So moment of resistance I am now considering with respect to steel. Now you see MUR is equal to 0.87 Fy AST D minus 0.42 XU, just whatever expression. Now this expression I am doing some manipulation. Now see here 0.87 Fy AST D minus 0.42 XU. XU we had already obtained 0.87 Fy AST divided by 0.36 FCK B. So that I substitute here. Then if you simplify it, you will get 0.87 Fy AST D minus Fy AST by FCKB, and further if you assume simplify, so this expression you will get. That means we will get MUR is equal to this 0.87 Fy AST D minus. Okay, why I have done all these things? This expression again, it is available in IS456. So don't worry, you need not be worried. Whatever expressions you will be required for solution of the problem, it is available in IS456. Only thing we are doing all these things, how these expressions are arrived. Okay. Anyone? Give your view. Anyone? All of you are listening?
Yes, sir.
Yes, sir.
Yes, sir.
Follow something. I don't want that you are to follow 100%. Something, that some new thing you are getting. Yes or no? You may not follow, but I expect that at least 0.1%, whatever I am talking, you are following. Yes?
Yes, sir.
Do not expect 90%. If you follow 0.1%, then also I will be satisfied. Okay? So one expression we had got, one expression we had got. This expression is available in your code. After this, we will try to find out some expression, because at the time of solution of the problem in your academic life or in your real life, this expression, because the same with the help of one or two expressions, we may not be able to solve the problem. So different expressions we may require at different time, at different time. Now say, what is this? Say percentage of steel. This AST. This AST, area of steel, amount of steel. How we can relate this amount of steel with respect to the cross section? With respect to the cross section. Cross section means width of the beam and effective depth of the beam. Width of the beam is small d, effective depth of the beam small d. So with respect to this, so that we will be able to do with the help of a non-dimensional factor. AST, its unit is millimeter square. If B is in millimeter, D is in millimeter, and B into D, it will be in millimeter. Okay, so we want to relate BD with AST. We want to relate it. So if we want to relate it, we require a non-dimensional factor. A factor which is not having any dimension. So that non-dimensional factor is percentage of steel. Okay, now see here, we are taking this. Is the percentage of steel, AST by BD into 100. So how we arrive this expression? I think you had learned in your class 10 standard. This is not, I will not say that you had learned in your first semester, second semester, third semester, fourth semester. No, this in different form. Only thing is in different form. This you had learned in your class 9, 10th standard. Okay, so now whatever expression we had got in our code, MU what? Moment of resistance. MU is factored moment of resistance. MU is the factored bending moment. M capital M suffix capital U, it is factored bending moment. And M suffix capital U capital R, like this U and R not necessarily be always U and R. It is some authors utilize small letters, some authors utilize capital letter, but I like capital letters, so that's why I'm writing this. Not necessarily, but you ought to write. Okay, so that expression, you bring that expression 0.87 FYASTD 1 minus FYAST FCKBD. Now here you replace AST by percentage of steel. AST by percentage of steel. Now see here, what I have now, 0.87 FYASTD, 1 minus this, no, 0.87 FY. Fy. Now this AST is replaced. First FCT is replaced to P by 100. So P by FCK, FCK, this is AST by BD is equal to P by 100. P by 100 and BD are coming out. Okay, this. Then finally, again, we are getting a non-dimensional factor. MUR by BD square is equal to this. Now the use of this non-dimensional factor. You will get in your textbook, if you had already purchased, some table or some curve. Some table or some curve. Okay. Now see here, on left hand side, moment of resistance, BD square. Now B and D are known to us. This stress in steel is known to us. Stress in concrete is known to us. Okay, so in this equation, our unknowns are MUR and P. MUR or P, according to our this equation. But on this equation, we may know MUR. How we know? We know MU. Equilibrium, the external moment must be equal to internal moment. So we can replace MU by MUR. So MU is known to us. MU is known to us. So from this equation, we'll be able to find out P. We'll be able to find out the P. Now, if once we know the value of P, which is our basic requirement for design of RCC design of the beam. Basically, in RCC design of beam, we have to find out the amount of steel required. Amount of steel required, because what is normally done? So MUR, MU, it is known to us. Okay, we will not solve the problem whatever the matrix is done. See here in this equation, if we go to for a mathematician, this MU only known is MUR. B, width of the beam, is unknown. D, effective depth of the beam, unknown. P, unknown. This Fy, FCK, these two are unknown by known. These two are unknown by known. Okay, that means what we can do, this Fy and FCK, we can assume, because we know there are 3 grades of concrete. Sorry, steel. There are 8 grades of steel. Any one concrete we can consider. Any one grade of steel we can consider. Once we assume grade of concrete and grade of steel, we can find out FCK and Fy from the IS 456. Okay, so Fy, FCK is known. So P, B, and D unknown. So we require 3 equations. If these problems you want to solve with the by the mathematicians or by your computer. So if there are 3, since there are 3 unknowns, so we will be required 3 equations. We have to create 3 equations. So it is a long procedure. So what we will do under this situation, because we are not student of subject mathematics, we are student of subject of design of RCC design. So what we do, we know many things, and what those things we will utilize. So what we will do, we will assume the value of B and value of D. So only unknown is P. Now by mathematical manual solution also, you will be able to find out the P. By manual solution also, you will be able to find out the P. So P by 100 into BD is the amount of steel. Finish. Then you will get some design curve or design table. Design curve and or design table, which is related with respect to mu by mu by bd square. The curve is there, mu by bd square. So in mu by bd square, you will get a numerical figure, and from that curve, from that table, you will be able to find out a point P. So utilizing that P, we'll be able to find out the amount of steel. Now, question arises. Question arises whether our aim is only to find out the amount of steel required. Whether you need to find out the amount of steel required. You'll get many problems. Sometimes you may have to check a beam, whether on that beam will be able to increase the load. So if you know the characteristic, you know the characteristic of the beam, you know the width of the beam, you know the effective depth of the beam, you know the amount of steel of the beam, you know the amount of steel of the beam, then you come to this equation, either this equation, or any equation, say come here, and you are equal to this anyone. You know the amount of steel, you know the amount of steel. So from this, you will be able to find out the MUR, factored moment of resistance. And for equilibrium, factored moment of resistance is equal to factored moment of resistance is equal to factored moment. Now you see the end condition of the beam, whether the beam is simply supported or whether beam is fixed. Let us assume that the load, whatever will come, it will be uniformly distributed load. If the load is uniformly distributed load, and if the beam is simply supported, then our aim is to find out the load. So we know if the beam is simply supported, load is W, then our maximum bending moment is WL square by 8. WL square by 8. Now this W will not be W. This W will be equal to WU. WU. This is the factored load. This what is factored load? It's up till now you had not learned. This you will learn in your structural analysis. Probably this will come in this subject itself. No, it will not come in this subject because this is the structural in the next chapter. Okay, so that you will get actually not small w but small WU. It is the factored load. Now this factored load, you have to divide by the partial effective factor, so you will be able to know what is the load that can be carried by that beam. It is a reverse way. Okay, then come next is again some factors we are trying to find out. Now see expression for XU by D for a given B, D, and MU. That means you know the effective section, you know the MU. MU is the factored moment. If factored moment and breadth of the beam and depth of the beam is known, then XU by what is the value of XU by D? Why we require XU is the actual neutral existence. We had got one expression at the very beginning, XU by D is equal to 0.87 Fy times AST divided by 0.36 FCK BD that we had got one expression. Okay, FCK by BD. So that for using that we will be required. XU by D is equal to 0.87 FYASD 0.36 FCK BD. Okay, now how to find out? Okay, now see, we had gone to limiting moment of resistance, or limiting neutral axis depth factor. This we had limiting neutral axis depth. From that, we brought this expression MUR is equal to 0.87 FYASD D 1 minus FYASD FCKPD. And this we have got in terms of percentage. Okay. Okay. Now see this expression and page 0.36 FCK BD square. 0.36 FCK BD square. Our actual expression was 0.36 FCK B into XU. B into XU. Now we have divided these things by D. That's why the XU maximum by D. Okay, please. Now see, then all this is MU. Now when this you are simplifying, XU maximum 1 minus 0.42 this is equal to this XU. Then equating this now here. Then we are getting CP. Now here, can anybody tell me? Oh, you are not looking. You are not looking. You are not. You are unable to see here. Here in this part, there is a big mistake. There is a big mistake. Are you hearing me?
Yes, sir.
This is the big mistake.
Yes, sir.
Can you tell me what is that big mistake? Can you identify or can you tell me what is the big mistake? No? The big mistake is that I had started with 0.66 FCK BD square into XU maximum by D. No, it is not XU maximum. This is my computer typing mistake. Computer typing mistake. This is XU by D. Whether just now I will be able to correct it or not, I don't know. This is the correct thing. Sorry. Huh? Okay. Okay. Now, some permutation combinations are made. Finally, we have got one expression, XU by D is equal to 1.2. Now, this is one important expression. This is one important expression that we are going to utilize. Okay. So this expression is after deduction. So this expression you will not get in your textbook. You can find out from this expression itself, but it is a long thing. But if you can somehow remember, so it is very simple. So XU by D. Now what we are getting? XU by D, we are getting some numerical value. We will get some numerical value. Right? Now why we are trying to find out? Now here see, this thing is dependent on FCK. The variable is FCK. If you change the concrete XU by D, we'll get some value. Okay. We had one expression XU maximum by D for 250 it is 0.53. For 415, it is 0.48. For 500, it is 0.53. Now you compare these two. This is XU maximum, it is the ratio. This is the ratio with respect to neutral axis. Neutral, actual neutral axis depth factor. And we had obtained limiting neutral axis depth factor XU maximum by D. Say if we are utilizing, say, Fe415 still. Now XU maximum by D is equal to 0.48. Now come to this fellow. If this XU by D, the value of XU by D is less than 0.48, then the beam is safe. If the value of XU by D happens to be more than 4.48, then the beam is not safe. Why safe? Why not safe? We will tell you just either today or next. Okay, for comparison, using this expression we can find out on this thing. Now come to the limiting moment of resistance. So this is with respect to actual moment of resistance. Now here I am writing, here it is correct. MUR maximum. MUR maximum. Maximum factored moment of resistance. And maximum factor moment of resistance is also called as limiting factor MUL. Okay, so this expression previously was with respect to our normal what we had defined design. Obtain 0.36 FCK B into XU bucket D minus 0.42 XU. Since here we are writing maximum or limit, so XU is replaced by XU maximum. Okay, so 0.36 FCK B into XU maximum. Okay, now this when you come to simplification, we are getting 0.36 FCK B XU maximum by D, 1.42 XU maximum by D. Now see here, that means MUR is equal to 0.36 FCK B D bracket 1 minus 0.42 XU maximum by D, right? Now XU maximum by D is a constant. So here you see MURD is dependent on what? B and D are constant, so it is dependent only FCK. Only FCK. Now you put the value of FCK. If you put the value of FCK, if you put the value of FCK, now here you see, I am not writing the value of FCK. Oh yes, if you put the value of XU maximum by D, if you put the value of XU maximum by D, so I told you XU maximum by D, if it is Fe250, if it is Fe250, it is 0.53, and if you put all these things, we are getting 0.148. Similarly, for 415, 0.138, and for 500, this. That means MU is equal to MU is dependent on FCK. Is dependent on FCK. Okay, so this we have obtained with respect to concrete. That similar expression we can find out with respect to steel, because we have already got one expression, moment of resistance with respect to steel, 0.87 Fy AST D minus 0.42 XU. Now if you replace XU by XU limit, XU maximum, then it will be in MUR with respect to steel. This previously what we had got with respect to concrete. Okay, so this we had obtained maximum pressure, limiting moment of resistance with respect to steel. 0.87 FYSD, D minus 0.42 XU maximum. XU maximum, what you do outside the bracket part, you multiply by D, and inside the bracket part you divide it by D. So ultimately what is happening? We are getting this D come out, this D come out. So here we are giving a D. So when this D come out, it should be divided by D. That's why this D. Then this D has come out. Because of that, this is coming, and ultimately this. Now these six expressions, you will be required in your academic purpose as well as working purpose. These six values you will not get in your school. You have to remember.